Yes.
So again, I want to be sure that no one is using metric or SI units. You cannot use it. Once you start use it, unfortunately, I'm going to be deducting some points in your homework. I've seen some people start to use it. I don't know the reason. I never put here any dimensions or any information on any of the examples in metric or in SI units. The ACI itself, usually it is written mainly for PSI system, the imperial system or the US system. And from time to time, they can just give you some conversion here. But I'm not going to be doing any analysis here in metric. I don't do it here. So be sure that once you start here to use metric or SI, you should expect that some numbers get be deducted um, from your homework. Also, when it comes to any moment, look here at the end results get being kip foot. Please do not leave it as a kip inch. You're going to be losing here some points for no reason. It's so simple, you know how to do the conversion. All moments is getting kip foots. All forces is getting kips. I understand that you can do it in pounds, but you need to convert at the end to being kips. This is going to be very important. Also, it's going to be very important if you say phi min or m sub u or whatever, any moment values that you put there, like any moment value. Let me look here for any moment value that we have calculated. Let's say for phi min. Once you put phi min and you give me a number, you need to put this, the symbols here. You need to tell me exactly, is this going to be kip foot or kip inch or what are you talking about? If you didn't put this, you're going to be losing at least half a point. I need to take it out because I cannot say that two people, one of them has put it in kip foot, the other one put it in pound inch, and he didn't even care about putting the units. So units in this case is going to be important. I cannot set both people here to be with the same grade. I need to have some differentiation between a person who knows, and you heard me before saying that it needs to be in kip foot versus a person who didn't put any units and left it for me as maybe in pound inch or maybe pound foot. I have no idea and just left it there as a number, and then you go figure it out. It's not going to work this way. So I hope that you guys understand this. You're going to be completing your work to the end. In this slide set number 5, we're talking mainly about T-beams. We didn't talk yet about W reinforcing beams. I'm just gonna go here quick to the last problem here. Last problem here. This is not a typical or a standard T-section that you're used to. Usually in a T-section, you're gonna have concrete slab on the top and then the beam is gonna be right below. In this case, what we have this piece that sticks up. And once you do your analysis here and you find out that your neutral axis or compression block depth A is going to be within the beam itself, you will figure out right away that you're going to have here two forces, two compression forces. One is going to be right on this tab, if you like to call it this way, and the other one is going to be for the rest of the beam. It's going to be two compressive forces. The stress over the entire area here in compression is going to be 0.85 F prime C. So if you have two areas here, if you like to call this A1 and this is going to be A2, over A1, you're going to have 0.85 F prime C. Find the force, you just simply multiply by A1. Same thing for the second area here. The second force, C2, is going to be 0.85 F prime C times A2. It's okay for you. You should be able to call it NCF on the flange, or just call it C sub F, or you call it C1. So I'm going to put here the options for you. It's going to be okay if you put the following. It's going to be either C as a compression force. You can also use C sub F, or you can use NCF. I'm okay with that. We put here a lighter background so that you guys is going to be able to see it nicer. Are you good about this? So use any of these symbols. So if you decide, let's say that you have a couple of forces here, then you're going to say, oh, this is going to be here, C1. How about this one here? I'm going to say, well, this one you can call it C2 if you want to. I'm okay with this. Okay. When it comes to compression block depth, it has to stay as an A lowercase. Please don't use A uppercase. A uppercase usually indicates an area, cross-section area. With that, I have my comments on this slide set and some of the homework. Now I'd like to hear questions from you in this slide set. You let me know if you have questions. Otherwise, I'm going to be moving here to the reinforcing, doubly reinforcing system. which we have it in slide set number 6, and consider that this is here complete, and you guys have asked all your questions. So now it's gonna be your chance to ask.
Can you explain how we got the value for phi using the graph?
The value for phi. Good question. No problem. In here. So I'm gonna take you back here to this analysis for quick. I'm gonna say that we have two forces. And since I did the preliminary analysis, I found out that this A is gonna be deeper than this HF. So HF here is equal to 4 inches. I know it's gonna be within the web. So I know that this analysis here is inaccurate. Why? Because this number here assumes that the block depth and the width is gonna be something like this, right? Why is that? Look at the equation. It says 0.85 A prime C times B. So the width I used in determining this A lowercase compression block depth, I used a small width 7 inches. This is why the depth is just big, 13.45. But I know for sure that compression block depth is gonna be in here, like in somewhere here. This is the reason I'm gonna be doing recalculating this A. So redoing A, and consider that I'm gonna have here one fixed force, the NCF. Why? Because the compression area is gonna be equal to 28 square inches. This is gonna be like fixed number. So NCF is gonna be fixed. It is not really based on this depth A2. And then say, here's the complete tension force is gonna be equal to NCF plus NCW. I know that NCF I can do it numerically. Also, I have the tension force. I'm assuming that the steel is yielding, and therefore I have the big tension force. The difference between the two is gonna be equal to NCW. Now take this NCW, you have numerical value for it, it's gonna be equal to A sub 2, lowercase, times the total width, 17 inches, times 0.85 F prime C to be equal to NCW. With that, you have only one unknown in your equation, which is A sub 2. Now the total depth for the neutral axis, look what happened here for the compression block depth. In this analysis with 13.45. Now once I assume the real distribution of the stress over this area here, now I have 7.89 inches. Said, all right, good. Now I have the total neutral axis depth. Now I need the C lowercase. What is the C lowercase? It's gonna be the depth of the neutral axis. So neutral axis is gonna be happening here. So I'm gonna say the distance from here to there is gonna be called C lowercase. So let me put it from here. I'm gonna say all the way to here. Now this is gonna be C lowercase, right? So I'm gonna put it right there, C. So C is related to A. Now where is A? I'm gonna say this is here A. So A is gonna be the 7.89. This is gonna be A lowercase. And this is equals to A1, which is 4 inches, plus A2, which is 389. Now what's the relationship between this C and between A? You can say this is gonna be simple, because A equals C times beta 1. You guys know this equation, this here beta. Now I have A, I solve for it, and I'm looking for C. So you can say here that C equals A divided by beta 1. And with that, I'm gonna have the depth of the neutral axis. So I said, okay, fine. Let me find this depth C. So let me do it here. Here's the depth C. It's gonna be equal to A divided by beta 1. Beta 1 in this case, 0.85 for this concrete strength. How much is the concrete strength in this problem? Anyone recalls? It's right here, 3 KSI. Yeah. So beta 1 is 0.85. You wanna confirm this? Look here. 3,000 means this is gonna be the strength of the concrete. Let's say maybe about here, somewhere here, which means beta 1 of 0.85. It's okay. Your C distance is gonna be 9.28 inches, 9 and 28 inches. One of the ways to find out the phi factor is to find the ratio C over D. So I'm gonna say, okay, how much was the depth? I'm gonna go back one slide, 2 slides here. The depth is 24 inches. And D is 9.28 for the C, right? So C over D It's going to be 928 divided by 24. I have a ratio of 0.386. So, okay, 386. Where's the 386? Now, which one is this? You're going to say, which value is this? What's C over D ratio that you have in here? 375. How about C over D value here? Say 0.6. So where is this that we're talking about? 0.386. Do you think it's going to be in this side, transition to tension control, or transition or compression? 386, it has to be in here. This is actually the solid line. It's going to be 0.386. You have this graph, we are working with the solid line, and the phi factor is lower than 0.9. So you either can read it off the graph, if you are able to, or you can just use this equation. Let me put in the box. Equation says take 0.65 plus 0.25, 1 over C over D, subtracting 5 over 3. And with that, you have the phi factor. So this equation here is going to be for the transition only. And also you have it here. So if you have, let's say, the strain and the steel, someone else is going to say, I'm not going to do it this way. I prefer, instead of finding C over D, to find out the tension strain in the steel. You guys know how to do the tensile strain, the tensile strain in the steel. The way you do it from these two similar triangles, right? You look here at the strain distribution. I'm going to say strain is going to be right here. This is the strain, right? This is going to be the datum for the strain. And this is going to be the strain distribution is going to look like this. So you can say 0.003, which means the strain in the concrete on the top. Divide this by C. And how much is C? 9.28. This is going to be equal to the strain in the steel divided by D, 24-inch, minus 9.28. Two similar triangles. So you should be able to find out the strain here in the steel. Once you find the strain in the steel, you can use this equation. Look at this equation here. You can use it. This equation, it gives you here the y component on this axis, the phi factor, equals to 0.65 plus the strain in the steel subtracting 0.002, multiplied by 250 over 3. So you have here two ways of doing the strain and the phi factor. One way to do it when you do the strain in the steel, the other method when you do C over D. Did I answer your question?
Yes, it did. Thank you.
No problem. Any more questions? Any?
Professor, what is the difference between these two equations, spiral and other?
Same. One of them is going to be based on the strain in the steel. So if you have the strain in the steel analysis or calculation, you can just use it in this equation. And this one here, you just do C over D, but they're the same.
But I mean, what is the difference between the two equations for C over D?
This one, and this
Yes.
one?
Yes.
Oh, this one for the spiral. What is a spiral curve? The spiral curve is going to be this curve. You see the spiral? When you have a round curve, it says here spiral. Here it says other. You see this other? It's going to be for this curve.
Thank you.
We're not handling here any spiral columns. So I'm going to say let's use other, the solid line.
Thank
All right?
you.
No
Professor, I'm assuming that spiral columns are weaker than just a regular solid column.
Not really. They are stronger.
Oh,
If you have
really?
the same, yeah. Because the spiral itself, it provides more confinement to the concrete. We're going to be talking about this in column design. I'm going to show you the two equations.
Professor, so we would only apply either those two equations to find phi if we were within the transition zone?
Yeah, use one of them. You don't have to use both of them, right?
No, but for example, if we were in the compression zone, it'll be the phi would be
0.65.
Okay.
Yeah, so for example, if the strain is going to be within this, and we have an example on this, right?
Mm-hmm.
You remember which example or what's it?
I forgot which one.
Here it is. Just take a note, please, of this. It's going to be slide set number 3. It says RC section. And in here, what happened, we start with a given section. We say 3 number 8. And then I said, well, 3 number 8 is good enough, but let's say I need more capacity. So what I did, I added a lot of reinforcing. Instead of 3 number 8, I made them 10 number 8. I want to see what is the effect of this, right? And we're trying to compare here what happened to the phi factor. So what happened when you add lots of reinforcing, the compression block depth went down, right? And C over D was very big in value. So what happened in this case? The phi factor was 0.65. And the total nominal capacity, look what happened. 133 for the capacity of the section, 103.7 phi man. But in the previous problem, when I have just 3 number 8, look at the trends. It was 121. So I added lots of rebars, but I didn't gain lots of strength. I was expecting when I add 2 number 8 versus 3, that I'm gonna have increased maybe 3 times. Think about it this way. You put 3 bars and then you add, after this, you add, let's say 7 bars to them, or even 6 bars. So you say, I tripled the strength. I added 3 times the amount of rebars, right? But guess what happened? 121 with the capacity, I increased it to only 133. It didn't go 3 times because the strength of the concrete was reaching the capacity here, and then you start here to treat the problem differently. Now you have compression control failure, and in this case, the phi factor has dropped down. Instead of using 90% of the capacity, now you're using 65% only of the capacity. And this is the way that you lost the strength.
Professor, one
Yes.
more question. For the area of the steel, I was looking up equations because I completely forgot about the steel graph that you gave us. But is it okay to have the formula where I think it's, for example, number 8 steel? I know the diameter is 1 inch, and then we multiply that by pi to get I think the area of steel. That's what I did on the homework.
That's not good.
No?
No, this is not the way you do it.
Hmm.
This is why even the ACI, look at the end of the ACI. They say this is give you the cross-section area of the rebars according to the ASTM 615. And you need to use it.
Okay.
Yeah, be sure that you don't repeat this. Okay. All right. Now I'm gonna go here to slide set number 6. So are we good with slide set number 5?
Yeah.
We're done with it. These sections are okay. All right. Slide number 6. What happened here? We're gonna have compression reinforcement on the top of the steel beam of the beam. So all of a sudden now we're gonna be adding this row of reinforcing. I understand that we still have positive bending moment, which means tension is gonna be at the bottom and compression is gonna be in the top. Generally speaking, usually you're gonna be adding some steel on the top. Why? Because if you have a tie, you cannot just put the reinforcing here, put the tie, and leave it here without tying it to anything. It's gonna be falling aside, you know. But also this reinforcing here can help a little bit in the strength of the beam. So having something in the compression is gonna help you out. So let's go here through the symbols that we're gonna be using in our analysis. The width is gonna be B, it's gonna stay the same. Depth from the top of the compression to the tensile reinforcing is gonna be D. No change. AS is gonna be the cross-section area of the steel in tension. Now here are 2 new terms that we are adding. One of them is gonna be AS prime. Once you see here the prime, it means something is gonna be in compression. So AS prime is gonna be something new that we add to the picture in analysis. Other thing also is gonna be D prime. Look, definition of D prime. D prime is gonna be the distance from the same top compression fibers to the compression rebars. So we have here 2 terms, D and D prime. D to the tension rebars to AS, D prime to the compression rebars, AS prime. This gonna be the 2 new items that I need to introduce here. So, okay, what does it mean? Now let me put all the forces. To find out the forces, first you need to have the strain distribution. So the strain is going to be uniform like this. The strain in the concrete is going to be 0.03. For any capacity point analysis, the strain in the concrete is going to be set to 0.03. The C lowercase is going to be neutral axis depth, as it says here, neutral axis. This is going to be C. Compression block depth is going to be a little bit smaller. Look at this, slightly smaller. The strain in the steel is going to be called epsilon S. And usually we like this to be at the yield point. So usually we start by assuming that the steel is already yielding. So this epsilon S is going to be equals to epsilon Y. And therefore the stress in the steel is going to be equal to F sub Y. So fine, that's good. So based on this, you should be also able to find out the strain in the compression steel. I'm going to call it here epsilon S prime. Everything that has prime here, it means it's going to be in compression. AS prime is going to be in compression. D prime, depth to the compression reinforcing. Epsilon S prime is going to be what? It's going to be the strain of the compression steel. Since you're going to be dealing with the steel, whether it's going to be intentional compression, you'd like at the beginning to estimate or to think that maybe the steel here has been yielding in both tension and compression. This is going to be the first estimate because you'd like to simplify it at the beginning. You don't like to see lots of unknowns at the beginning of the problem. Now let's look at the forces. The strain in the steel, if this is going to be epsilon S, the tension in the steel is going to be equal to the total cross-section area of the steel multiplied by F sub S. What is F sub S? F sub S is going to be equal to the stress in the steel based on this epsilon S. If this epsilon S is going to be equal to epsilon Y, yield point or more, this F sub S is going to be equal to how much? It's going to be F sub Y. Let me put here the stress-strain relationship for the steel. For any epsilon sub S within the elastic range, like in here, you can solve for F sub S. Once the strain in the steel would become equals to the yield stress or more, which means like in this location, the stress is going to be equal to F sub Y. We understand that this is the actual stress-strain relationship for the steel or the actual performance. But in our analysis, we assume elastic plastic. What is elastic plastic? Means that we assume this is going to be a straight line all the way to here. This is going to be our analysis, is going to be based on this. And once you hit the yield point, it's going to be straight like this. Take it from this side. It's going to be like this. So we don't really care about the strain hardening in our analysis. We say if the strain in the steel is going to be equal to epsilon Y or more, the stress is going to be equal to how much? We say it's going to be equal to F sub Y. It's going to be straight. It's going to be constant. This is our assumption when we treat the stress-strain relationship for the steel. So I'm going to say here, for any given epsilon S, I'm going to have F sub S. This F sub S, in some cases, is going to be equal to F sub Y. Other cases, it may not be equal to F sub Y. Now I'm good. Now I know this force here. Done with it. Say, how about the compression? You can see now compression, you have two components. You have the concrete and you have the steel. The concrete one is simple. It's going to be 0.85 A prime C AB. I'm going to call this A1. C1, which is compression in the concrete. And of course, it's going to be happening for a depth that's going to be equal to A that I don't know it yet. I need to determine this depth A. You're going to have another force here, which is compression in the steel, is going to be equal to the stress in the steel, in the compression steel. So in this case, I'm going to be calling it F prime S. Multiplied by the cross-section area of the steel, AS prime. Yes, okay, now I have two forces. It's good. Now the other thing I need to know is going to be the Z distance. Z distance is the distance from tension to compression. Why do I need it? To find out the moment acting on the section. The internal moment, which means the strength of the section. Is it great? Where is the first force? You can see here's the first force. C1 equals 0.85 A prime C times A times B. Good. What is the Z distance for it? I'm going to say this can be the same as the one that we have done before. There is no difference here. It's going to be D minus A over 2. Reason, here's the depth from this point to the top, and from here to the center of the compression block, it's going to be A over 2. So it's going to be D minus A over 2. We're done with this Z1. How about Z2? The distance to the second compression force. You can say, well, this point here is fixed because it's going to be at D prime, distance from the top. So the distance from the tension reinforcing to the compression reinforcing is going to be equal to D minus D prime. It's going to be constant number. It's going to be fixed number here. It's not going to change with the change of A. Now, if you like to write your equation for the moment, capacity of this section, we're going to say M sub n equals C1 times Z1 plus C2 times Z2. Make sense? Yes? This can be very similar to the equation I used for the T section from here. This equation. Same equation. C times Z plus C times Z. And then at the end, of course, for the phi factor, you just multiply here by the phi factor. It's exactly what I'm doing here. At the end, I'm going to have here phi factor. But at the end of the analysis, I'm going to have two compression forces, and I have two Z distances. So I need to multiply Z times C. That's it. Any questions at this point?
Professor, can I ask a question?
Yeah, of course. That's what I'm urging you to do.
Okay. Is the Fs prime the same as Fs? Because the steel is compressed for Fs prime. So I'm confusing whether it is the same.
Okay. The steel stress-strain relationship for tension and compression is the same. This is what you need to know.
Okay.
So, for example, if I said epsilon S was found to be here. So for epsilon, usually epsilon you know is the same as E, right? So I'm going to say here ES. ES means epsilon S, right? So I said here, you're doing the analysis. So go to the same stress-strain relationship. Find out epsilon S. Okay, you go with the straight line. Oh, it turned to be here. It's more than epsilon Y. You're done. Here's F sub Y. For the same section, what I want you to do is to find out epsilon S prime. So I'm going to put it right here. Epsilon S prime. Just for an example, right? You put here epsilon S prime. It was lower than the yield strain. And how much is the yield strain? Anyone recalls this? Very rough number.
0.002.
002, right?
Yeah.
Okay, good. Very good. How can I find this numerically? If I don't know, I'm going to say it's going to be equal to 60 divided by 29,000, right?
Mm-hmm.
Is this the same if you have grade 75 steel? I'm going to say no. For grade 75 steel, it's going to be equal to what?
75.
Yeah, it's going to be 75 divided by 29,000. Very good. So for grade 60, this is going to be this number on the top. So let me put this here. I'm going to say grade 60 steel. What's going to happen? This is going to be the strain value, the yield strain, 0.002. So in this case, I'm going to be looking here at the strain that you figured out or you calculated out at the compression steel. Take the strain here, multiply by 29,000, which means ES, the modulus of elasticity, and with that you get the stress in the compression steel. So in here, you're going to have, this is going to be the value of, when you go horizontally, this is going to be Fs for the tension steel. For this value here, you're going to be getting Fs prime. It's going to be the compression stress in steel. You're good?
Mm-hmm.
John Quinn, did I answer your question?
Yes. Thank you,
Okay.
Professor.
Thank you. All right, good. All right, now back to our equations here. So I guess the equations are simple. We don't know how much is epsilon s. We don't know how much is this epsilon s prime. So as usual, we like to simplify the analysis. So I'm going to assume that the tensile steel is yielding and the compression steel is yielding. And then after I assume this, I'm going to do my analysis and then determine the strain in the tension steel and compression steel and see if the steel was really yielding or not. Which means I need to prove that the steel is yielding. Otherwise, my assumption is wrong. And I need to redo the analysis. All right, are we good about this?
Yes.
All right, great. Look here at this tension force. This tension force is equal to AS times FS. I know that this tension is going to be equal to C1 plus C2. Which means I have one couple here because I have two couples, right? A couple means a moment. So one couple is going to be equal to C1 times Z1. The other couple is going to be equal to C2 times Z2. As if this tension force here is going to be composed of two tension forces. One of them is going to be equal to C1 and the other one is going to be equal to C2. So, okay, yeah, this makes sense. Now let me split it. I'm going to say, I'm going to have here two tension forces, two compression forces. So looking here at this diagram, everything is the same. Look at the strain, everything is the same. Looking at the force, now what happened? I have taken this force diagram, split it into two diagrams because I have here two couples. The first couple is going to be related to the compression in the concrete. So I'm going to say here C1 is going to be equal to T1. And C2 here is going to be equal to T2. But my understanding also that T1 plus T2 is equal to what? I'm going to go back here one side. It's going to be equal to this tension force, right? It's going to be one force at the end.
Just as a quick reminder, so the concrete steel couple is from the bottom of the concrete to the
Bottom of the concrete. Where's the bottom of the concrete? You mean here?
At the base of.
Bottom of concrete is here.
Yes.
We don't use this in our analysis.
Oh, no. Oh, okay. So
you'd like to say from the center of the tension reinforcing.
Got it. Center.
Yes.
Mm-hmm.
So this one, I don't want to use it because the concrete here is going to be cracked in the cover.
Mm-hmm.
So I'm going to be saying here that I have two tension forces, right? It's going to be equal to AS. Usually we assume that the steel is yielding. So I'm going to say here AS times Fy. And the other section or tension is going to be AS2 times Fy. But you know what? AS1 plus AS2 is going to be equal to this AS. I just split the force in the tensile reinforcing into two forces. Why? To work with two couples here. So I'm going to say here AS, the one that we just done a minute ago, now it becomes AS1 plus AS2. Is it fine? My first assumption to come up with this AS1 and AS2, if I say that the steel in the top here is also yielding. If the steel is yielding here, and this C2 is going to be equal to T2, and it's going to be equal to AS prime times Fy, it means that AS2 is going to be equal to AS prime. So this is one way of thinking about how to split the force here into two forces. Is to consider AS2 to be the same as this AS prime. So once this section here is going to be given to you, you're going to say AS2 equals AS prime. And AS1 equals AS minus AS prime. Does this make sense? Or no? Yes? Anyone get that?
Mm-hmm.
So at the beginning, all what I have is just AS. But I'd like to split this AS into two areas, AS1 and AS2. The simplest way, if I assume that Fs prime is going to be also yielding, I'm going to say here AS prime equals to AS2. At the beginning, when the problem is given to you, you have just AS and S prime. You don't have AS1 and AS2, and you'd like to come up here with AS1 and AS2. So the simplest way is to assume that AS2 is going to be equal to AS prime. Therefore, AS1 is going to be equal to the difference between AS and AS prime, because I know from the beginning that AS is going to be equal to AS1 plus AS2. Now, once you set AS2 is going to be equal to AS prime, it means AS1 is going to be equal to the difference between AS and AS2 or AS prime. Let's see how this is going to help us in our analysis. All right. We have an example. It says complete the moment strength, Pman, for the beam having a cross section as shown in the figure. Use F prime C is going to be 5,000 psi, and the yield strength is going to be 60,000 psi. Information provided. The width is B, 11 inches. Depth to the steel reinforcing, to the tension reinforcing is 20 inches. Depth to compression steel, 2.5 inches, given. There is no calculations here for it. Reinforcing tension, 3 number 11. Reinforcing compression, 2 number 8. Here's AS prime, here's AS. They give you all of that. They give you here a stirrup or a tie of number 3 with 1.5 inch clear. Is this important for me when I do here Pman? I say not really. You don't need this piece of information. Not in this analysis. Here's also my reason. The depth is given you directly to the center of the rebar. So this is not going to help to figure out the cover and figure out D. I have all of this information provided to me. Okay, let's see here the solution. Now in the solution, if I want to find out A, I need to set C is going to be equal to T. That was the only reason that I'd like to see this T1. Because determining the depth A, you need to have AS times F1, Fy. And it's going to be only AS1. I'm going to go back here a couple of slides. I guess now you appreciate the idea that I'm splitting here the tension force into two forces. Because if this force is going to be equal to that force, I'm going to be taking this out on the side. I can say T1 is going to be equal to C1, and for that, I'm going to be determining A, compression block depth. If I'm going to go here back one more slide, with this analysis that you're looking here at, how else would you figure out the compression block depth? Because if I'm going to be saying here T is going to be equal to C1 plus C2.
Wouldn't we be able to use the moment down below with the C1 times C1?
Yeah, but how would you find out this A? Usually in our analysis, we do A analysis, right?
Mm-hmm.
We say compression is going to be equal to tension. Now you don't have it, right? When you have just one force here, you don't have it. Unless you say C1 plus C2 is going to be equal to T. And in this case, the tension force is going to be equivalent to C1 is going to be equal to what? T minus C2, correct? If I'd like to do here the depth of the compression block analysis, you can say T equals C1 plus C2, correct? This is the analysis I need to do. Now you have the tension force and you have C2, correct? You're going to say this tension force, I have the value. So I'm going to say, yeah, given. It's going to be equal to what? AS times Fy, correct? Let me move it up a little bit, just for sake of discussion here. This can be the tension force, equals to what? Compression 1. How much is compression 1? 0.85 F prime C times B times A. Plus, how about C2? Do you have C2 value? So yeah, I have it. AS prime times FS prime. Great. How would you solve for A? You need to come back here and work on your equation and say AS times Fy minus AS prime times Fs prime equals 0.85 F prime C times B times A. Am I correct? Yes? Are you guys following me? All right. So in this case, you can solve for A. But you need to get rid of this section of it. So this is actually going to be called T2. And this one is going to be called T. And the difference is going to be equal to T1. So this here, I'm going to come here and say this is going to be equal to T1. And this section is going to be T2. T1 plus T2 is going to be equal to the tension force T. Exactly what I'm doing here. I'm finding out here T1. Look at T1 here, AS times Fy. Yeah. Just AS times Fy is going to be equal to the tension force, right? But T1 is going to be equal to AS1 times Fy. And T2 is going to be AS prime times Fs, which is this one, right? It's going to be equal to T2. So T, the force tension T1 is going to be equal to the total tension force subtracting T2 to set it equal to this guy. So either that you split it in this graph or you do this analysis, whichever is easier for you. So if you are good with this analysis, it's great to understand what I'm talking about. If this analysis is not clear to you, just look at it this way. Any questions now about this? About the idea of splitting the force into two forces? Or just thinking that this tension force is going to be equal to C1 plus C2. You put it in the same equation, you solve for all of these parameters, and then you leave your A to be your unknown. You have one of these two methods to handle it. Any questions? We're good? Move. All right. So my target here is to have just T1 and to set it equals to C1 so that I'm going to be able to solve for A. I said, okay, fine. Here's the analysis. AS2 is going to be equals to AS prime. And how much is this AS prime? You guys have it? I'm going to go back here. AS prime is going to be 158. And total AS is going to be how much? 468. So I'm going to say here, AS2 equals 1.58. Right? AS1 equals how much? The difference between these two numbers is going to be equal to AS minus AS2. Why? Because I understand that AS equals AS1 plus AS2. Right? Therefore, AS1 equals 4.68 minus 1.58. Yes or no? We're good about this.
Yep.
All right, great. This is exactly what I have here. Here's the analysis. 468 minus 158. Exactly what I have here. 468 minus 1.58 is going to be 3.10 square inches. Now, this is going to be your AS1. Now, go back here to this graph. Set this tension force with AS1, set it equals to C1 to solve for A. Set fine. I'm going to be doing my equation here. AS1 times Fy, because I'm assuming it's yielding, right? Divide by 0.85 F prime C times B, the 11 inches, and the 5K sign. Now I have compression block depth now is going to be 398. This is good, right? Now I was able to find out the compression block depth. Now what you need to do next is to find out the strain in the steel. Because guess what? You assumed here that the steel is going to be yielding, and you need to prove otherwise, right? If you prove that the steel is yielding, this is good. Your analysis is great, you're done. You can just find out the moment. If not, you're going to have here two equations, two unknowns. And you know the story about these two equations, two unknowns. Which means more analysis. So to find out the strain, I need to find out the C. Neutral axis depth. How do you do this? You divide this by beta 1. Now beta 1, when you have 5,000 psi, is going to be equal to 0.8. It's going to drop down. And you guys, you are aware of this graph, right? Beta 1 graph?
Yeah.
Once you go 1,000 above 4,000 psi, you're going to have a drop in the beta 1 of 0.05. So I said, fine. Okay, now I have it. Now find out the C, neutral axis depth, turned to be about 5 inches. So it went from 4 inches for the compression block depth to 5 inches. So what to do next? What to do next is to find out the strain based on this compatibility thing that we usually do. Can I say the strain on the top here is going to be 0.03. The depth of the neutral axis is going to be 5 inches. Location of the compression reinforcement, how much was that? It's going to be D prime, which is how much? Anyone recalls this?
2.5.
2.5 inches. How about the total depth? How much was the total depth?
20 inches.
Great. Okay. Now let's do the analysis here. First, I'd like to find out the strain here. How much is the strain here? I'm going to say the strain here, right, divided by 0.03, or the strain divided by this distance, which means C minus D prime. Look at this. The strain in the steel and compression divided by C minus D prime, the distance from here to there, is going to be equal to 0.03 divided by C. So everybody follow me in this? Finding out the strain in the compression steel?
Yeah.
So what I'm saying is going to be 0.03 compression strain in the concrete divided by C, neutral axis depth is going to be equal to epsilon S prime divided by C minus D prime, which means this distance. I have the equation right there.
The D prime is just right where the red line is, right?
Yes.
Yes.
Yeah.
Okay.
I'm going to take you back to this. Let's give you right here. It's right here. You see this D prime?
Mm-hmm.
This is going to be the depth of the compression reinforcing. So fine. Here is the strain in the compression steel, 0.0015. Now, question to you: is the compression steel has yielded already or not?
It didn't yield because
It didn't yield. Yeah. How much is the strain in the steel for it to yield? Epsilon Y for the steel is equal to 2.
0.0021.
Yeah. So the steel here is not yielding yet. How about the strain here in the tension steel? I say, well, let's do the same equation that I have used before, right? 20 inches can be the depth minus C, which is about 5 inches, divided by C times 0.03. The strain here is 0.009. This is good. The steel yielded already. So tensile steel has yielded, compression steel is not yielding yet. Okay, this is good to know, because now I need to refine the tension or that I have in the steel and the compression that I have in the concrete in the compression steel. Now, if the steel is going to be in this big tension strain, it means for sure it's going to be yielding. So there's no doubt about it, right? But for this strain here, the steel is not yielding yet. I need to figure out the stress in the steel. But I did something wrong here at the beginning. In my step here, in this analysis, to be able to say that I'm going to be splitting the force in this fashion, I assumed here that the steel in the compression is going to be also yielding, but this is not true. You see, at the beginning of the analysis, I said both the steel is going to be yielding. Now I find out that it's not really yielding, which means my equation is not accurate. So now I need to do more analysis to correct it. So I'm going to be doing this equation. You remember this equation that I started with? I'm going to go back here a few slides, just in case if you forgot about it. Here is going to be my equation. T is going to be equal to C1 plus C2, the very main equation. I tried to simplify it here by doing this analysis, say the steel on the top and the bottom is going to be yielding, just to confirm that the bottom is going to be yielding, because in some cases, the steel on the top and the bottom is not yielding. But now I confirm the bottom steel is going to be yielding, the top is not yielding, but my analysis is not very accurate. So I'm going to move forward here to this analysis. So, okay, now that was the main equation.
Professor,
Yes.
how did you come to that conclusion that the steel in the compression is not yielding?
Very good question. So what I did in this slide, I did the strain compatibility analysis. Are you following me? Yes, Oscar?
Yes.
Okay, good. How much is the strain in the tension steel? Can you read it for me, please? Can you see it here? Is it here somewhere?
Yeah, it's that one, 0.09.
Okay, good. Is this above the yield point?
Yeah, it's greater.
Okay, by a lot.
Yeah.
Which means if I'm going to be doing here any changes in my analysis, like if I'd like here to refine my analysis, do you think that this answer is going to change to the point that is going to be below the 0.002?
No.
No way, right? This is like 4.5 times. There is
Yeah.
no way. So this confirmed it here. So I know that this here yielding, right? The steel is yielding. How about the strain in the compression steel? Do you see it here somewhere on this page? You see the value?
Yeah, it's less than.
Okay. So I know that the compression steel is not yielding and the tension steel is yielding. So the first assumption I started with was incorrect, partially. It is true that the tension steel is yielding, but compression steel is not yielding yet. All right, we're good?
Yes.
Okay, good. So the simplification started with, I cannot really do it. So what I need to do is to start with this equation here, right? Knowing that the tension is going to be all, the tension steel is going to be all yielding. So this part of the equation is correct. This here is something that I learned based on this analysis. Otherwise, I would have just said AS times FS, right? It means that both of these two steels are not yielding yet. But now I confirm that the tensile steel is yielding, compression steel is not yielding. So I was able to refine my equation to this format. This here it says the tension steel is yielding. Compression number one, C1 is equal to 0.85 A prime C BA. It's going to be compression the concrete. And compression the steel is going to be based on this random Fs prime that I don't have the exact value for it. Now, let me put here in boxes the available information and the unknowns. I'm going to say all of this information is going to be available to you. Am I correct? You have AS, you have FY, you have F prime C, you have B. Do you have A? Not yet. Do you have F prime S? No. Do you have AS prime?
Yes.
Yes, I have it. I have a solid number for it. Maybe taking this and put here a box. How many unknowns I have in this equation?
2 unknowns.
1 and 2. Said okay. Can I put in terms of C and epsilon S? So I'd like to change them from having the two unknowns to be A and F prime S. I'd like to have it in C. What is C? Is it the compression force? C lowercase, neutral axis depth, right? And the steel strain and compression. This is going to be the two unknowns that I'd like to work with. All right. Why is that? I'll tell you the reason. This is because look at this strain compatibility thing. Can you find out here a relation between epsilon prime S and C based on this diagram? It seems that there is a way of doing this, right? Between C and epsilon S prime. Where is this equation that gives me here a relationship between the compression strain in the steel and between the depth of the neutral axis C? I'm going to say it's right here. We don't really need to go far, right? So in this equation here, what do we have? Where are the unknowns? Where are the knowns? Epsilon S prime is going to be your unknown. C unknown. D prime, we have it. It's like 2.5 inches. C is going to be the same unknown here. So I have in this equation two unknowns. Epsilon prime S and C. This is going to be one equation. Now where is the second equation here? I'm going to say, you know what? This here is going to be F prime S. And I know that F prime S is going to be based on the strain and compression. And I can solve for this easily. How's that? I'm going to say Fs prime is going to be equal to epsilon S prime times ES. So instead of having this F prime S, get divided by E sub S. With that, I'm going to have the strain here in the steel, in compression. Say fine. What's the relationship between A and C? Because see, this A, I can convert it into C. By doing what? By dividing it by beta 1. If I take this A, divide by beta 1, I'm going to have C. If I take this F prime S, divide by ES, I'm going to have the strain in the steel. This is great, because the other equation I have it right here. I have another equation between epsilon prime S and between C. Now I have two equations, two unknowns. All right, let's look at it. To get rid of A and use C instead, I'm going to say CA is going to be equal to beta 1 times C. Therefore, C is going to be equal to A divided by beta 1. Fine, this is good. How about for the stress and the strain in the steel? I'm going to say the strain in the steel is going to be equal to F prime S divided by ES. If I like to get rid of this, all what I need to do is just divide this term by ES. Now, where did you get this equation from? This is going to be the other thing that I need to ask you about. This equation here. Did you see this equation before? You can say yes, it's right here. It's going to be this equation. Look at this. Epsilon prime S divided by C minus D prime equals 0.03 divided by C. It's going to be right here. Same equation. This is going to be the strain in the steel multiplied by ES. You're going to get here to Fs. Meaning F prime S equals to epsilon prime S, the strain in the compression steel times ES. Said fine. Where is ES here? And take it and put it here, right? So what is this term here? I'm going to say this term is the strain in the compression steel. Where'd you get it from? From this equation here. Look at this equation. Strain in the compression steel equals 0.03 times C minus D prime divided by C. It's right here. Which means I combine here the two equations. This give me one equation and this give me the second equation. And for that, I should be able to solve for these two variables. When you combine these two equations, I'm going to make it here simple for you, because if I'm going to be going through all of this math, you're going to get lost. So I'm going to say at the end, I'm going to have this equation in terms of the two unknowns. This equation is good. So let me write this down so that you guys have it in the recording. This equation is good when? For what?
When the steel.
When Fs is equal to Fy, correct? When the bottom steel is yielding. And also what? Fs prime is less than Fy. So if you prove to yourself that the strain in the tensile steel is yielding and the strain in the compression steel is going to be right before the yielding point, you should be able to use this equation. You don't really need to drive this again for me. But if I were you, I'd drive for myself to understand what I'm doing here. You can just use this equation here. Let's look here at the variable in this equation. It says 0.85 F prime C times B the width times beta 1 times C squared. Now, where is the unknown? Let's say my unknown is going to be this guy here. C squared, right? Because I know all of these factors. I know F prime C, I know the width B, I know beta 1. Let's look here at the other variables. It says 0.003 constant ES. I have it 29,000. AS prime. I have it 1.58 in this example. Let me go back. It's going to be this 1.58 for AS prime or AS2. So all of this information, I have it. AS times FY. Do you have these values? I say yes, I have AS, I have FY. Here's my unknown, the second unknown is going to be C, right? Do you have D prime? It says 2.5 inches times 0.03 constant times ES, yeah, 29,000 times AS prime, the 1.58 equal to 0. So right now I have one equation and one unknown is going to be C, second degree equation. When can I use this equation? When you have this criteria or this condition. All right, I guess I should be able to solve for C. Let me put the values here. Here's the equation again written. So this can be the same equation. So either that use it in this format, or you can use it also. Let me copy this here again. In this format, it's fine. This is why I put it in this bluish background, kind of magenta background. What I did here, I substituted ES with 29,000. Why? Because I looked at this, I see here that I have ES, I have ES. Let me just take this ES out and put 29,000. And this equation is gonna be good. So this equation here is kind of general equation, and you can have it in your cheat sheet, your formula sheet if you like. And it shows here that you're gonna have here one variable, which is C2 and C1, and the rest of this information is gonna be known to you. So you have 0.85 A prime C, B beta 1, C squared. This is gonna be your unknown. Again, here's C, and this is gonna be the constant in your equation. So you're gonna have here one unknown, same unknown, first degree, and then constant. Here are the rest of the variables, parameters that you can input in this equation, right? AS, FY, F prime C, B, beta 1, AS prime, and D prime. You put it in this equation here. You put all of these values, and your equation will become, instead of this long format, is going to become much smaller. Now, here's the numerical value for this equation. You can solve it with this quadratic equation. Are you guys familiar with this equation? You know how to use it? We're good with it, right?
Yeah.
And usually you're gonna have two answers. One of them is gonna be like weird answers, something that you cannot really use because it doesn't make sense. It is beyond the logic. You cannot really use it. So it's a good answer based on this equation and based on this analysis is gonna be equal to 5.51 inch. Now, I don't want you guys to be confused with this A is gonna be equal to 1. This is not compression block depth, right? You guys understand this. This A is equal to 1 is gonna be for this equation. And this equation means it's going to be the factor for this variable to the second. And B is going to be the factor of this, which means it's going to be minus 3.38. This is not the width. And this C is going to be negative 9.19, right? It is not the compression block depth. So the weird thing here, that in this equation, you have the same variables, right? In our concrete analysis, we used A, B, and C. A is going to be compression block depth, B is going to be the width of the section, C is going to be neutral axis depth. So in here, it doesn't mean this at all. So please don't be confused between the three variables, right? And between the variables that we use in our concrete analysis. So at the bottom of the page, it says here, C is going to be equal to 5.51. So what is that? I'm going to say this is going to be what? Can someone help me with this? What do you call this C? What is that C? Definition of C is what? Neutral axis depth. Am I correct?
Yeah.
No one's going to say, how come here you're writing C is negative 9.19, all of a sudden you change C to 5.51. You're going to say, this two different C's. It just happened in the quadratic equation that we're using A, B, and C that we're also using in concrete analysis. Are we good about this?
Yeah.
All right,
Yes.
great.
Yes.
Great. Very good. Excellent. Very good. Now we have the depth C. What do you do after this? Say depth C, what I need to do is to find out the strains. Let's find out the stresses and the strains and solve the entire problem again. You see this section of the analysis? You see this section of the analysis? Up to here. Let's say up to here. I've just done this right here in this step. In step number 4, I did the same analysis, right? So this step, which is going to be number 6 and 7, I'm repeating exactly what I have done in step number 4. Just repeating it. Because what I'm saying now, I have the correct C. Look at the C that I did here. If you recall the C value that I did here, how much was the C here? Anyone recall the C value? It's about how much? 5 inches, the 498. Now look at the C value that after we have done good analysis, 5.5 inches. So the C value has been increased. So now the strain also needs to change and the forces need to change. So I'm just repeating exactly step number 4 in step number 6 and 7. So with that, I was able to find out compression block depth based on this equation. It's going to be beta 1 times C1 times C. And for the stress in the steel, I was able to do it based on the stress strain compatibility in the steel, right? I was able to find the strain in the steel. And once you have the strain in the steel, you multiply by ES. Or you can just use this equation. Someone's going to say, where is this equation coming from? I'm going to say, simply go back here and you're going to see it. You see this equation? Either that use this equation, or you simply find out the strain in the steel multiplied by ES. It's going to be one of the two. It's going to be up to you. This is exactly what I'm doing here. Here is the tension strain in the steel, right? It used to be 0.009. It dropped now to almost 0.008. So I'm saying this is good. So now I confirmed again for the second round that the steel in the tension is going to be yielding, and the steel in the compression it's not going to be yielding. I proved this to myself, and I was able to find out the stress in the compression steel. If it is yielding, this would have been what? 6 KSI. Because it's not yielding, now it becomes 47.5 KSI. Now I have two compression forces. Yes, two compression forces. I guess I know how to do this. C1, 0.85 A prime C, BA. I have all of these variables. It's going to be 206 kips. The compression steel now is going to be saying what? AS prime, the 1.5A, times the stress in the compression steel. I have a second force. The tension force, you can also calculate out this way, and it has to be equal to these two forces. If you add this to that, you end up with the 281 kips. Great. So what's next? I need to find out here phi man. Here's phi man. I'm going to have here two moments. Here's moment number one. It's going to be C1 times Z1. Yeah. Plus C2 times Z2. Yeah, I guess we have gone through this. And then what do you do at the end? You add them to each other. You say Mn1 plus Mn2. This is going to be one moment. This is going to be Mn. And look at this. I need to show it in kip foot. And then what do you need to do after this? What you need to do is multiply by the phi factor, the 0.9. And here's going to be the moment capacity of that section. With that, you are done for today. And I'm open for questions for just a few minutes. And you know that we're going to have an office hour maybe in 15 minutes from now. So if you have more questions, you can wait and log into the office hour Zoom meeting. Otherwise, just go ahead and ask now. Let's give you a small question.
So
Thanks, Professor.
if the steel wasn't yielded at the compression side, we were not required to do the step like 6 and 7, right?
If the steel is not yielding or yielding?
If it wasn't yielding?
If it was not yielding in the compression,
Sorry.
yeah. If it was not yielding, and this is actually what happened. So there's no F here because it was not yielding. What happened? The steel, let me take you back to this line. The tension steel is yielding, compression steel is not yielding because this value here is lower than 0.002. So this is what happened. And this is the reason that we have gone through all of this.
Okay.
If both the steels are yielding, if this is yielding and this is yielding, therefore the analysis that I have done here is correct and we're done.
Okay.
So you would be hoping here that the steel in tension compression is yielding so that we're done. So you don't have to spend more time doing all of this analysis, right?
Yes.
Okay. My advice to you, take this problem here and do an Excel spreadsheet for it. It's gonna make your life much easier. Especially that you have the equations. You have all of these equations. You can just put this equation in there.
Mm-hmm.
You can put AS prime, you put D prime, you put AS, you put the depth, the B, the F prime C, the beta 1, and the whole thing, and you just digit in all of these values. The good thing about this, if you put AS prime is going to be equal to 0, it's going to be like the regular flexure problem or moment problem when you have a rectangular section. This is going to help you out a lot, you know, when you do your homework, when you do your project. So it's going to be useful, the spreadsheet for you guys.
Okay. Thank you.
And you have here a good example so you can back check all your numbers here. Okay, more questions?
Yeah, sorry if the tension was not yielding and the compression was, would we still be able to use this equation?
No, equation's gonna be different. Because look at this equation, the way it was derived. But usually this will not happen. Usually the tension steel is gonna be yielding and the compression steel is not gonna be yielding. This is expected.
Okay, thank you.
No problem.
Professor, is there homework this week? Or
Yes.
Is it up?
Yes.
Okay.
Yes. It will be possible. All right, guys. I'll see you in the office hour. Okay. Have a good night.
Thank you, Professor.
Can I ask something real quick? Just like,
Give me a second, please. Give me a second. Just a second, please. Yes, I'm here. Go ahead.
for the 318 code thing, is it okay to have it on an online copy, or do we have to get it as a physical copy?
It's gonna be up to you. Any copy is okay, as long as you have an access to it.
Oh, okay, okay.
All right.
So if we have an online copy, does that mean we're able to use our tablet to take the test, or does the test have to be taken on paper?
Okay. When you take the test, I'm gonna give you all the equations you need and all the formulas and all the graphs.
Oh, okay. So, okay. All right. Thank you so much.
No problem.
Okay, thank you.
No problem.